Welcome. Welcome to Module 4 of Part 1, which deals with refrigeration cycles. In this module, we'll cover implementation of the cycle in detail, especially vapor compression cycle. We'll solve a problem manually and verify using test help. And the prereq for this module is Part 0 of the same module, where we discuss the basic refrigeration cycle in terms of a closed steady system. And in module 3, we covered the PC model, so you make sure that you are familiar with that. And in module 2, part 0, we discussed open steady devices. So we'll draw upon all the knowledge from these different sections in this particular module. Okay, so let's get started with an implementation of the vapor compression cycle. Well, a cycle means you can start anywhere and go around and come to the same point. So let's start at point 4. Let's say we have a very cold saturated mixture of liquid and vapor, state 4. Very cold. And our cold region is TC. Let's say we want to maintain it at 0 degrees Celsius. So suppose at state 4, the liquid vapor mixture is really cold. Let's say it's -5 degrees Celsius. It's a liquid vapor mixture. As it enters what is called an evaporator, which is another name for a boiler really, it finds a very hot surroundings around it. Notice that this fluid is at -5 degrees Celsius and the region around it is at 0 degrees Celsius. So obviously heat is going to flow from the cold region to here, and that's our Q dot C, the cooling load we discussed before. So as heat enters the evaporator, the liquid inside evaporates or boils, and as the phase change occurs, we follow a constant pressure line. As heat is added, the pressure doesn't change in the evaporator, just like in a boiler in case of a steam turbine cycle. So from 4, the state keeps moving to the right without changing its temperature until we reach state 1, where we have, this is the G state, which means it's a saturated vapor at state 1. So what happened is that we picked up a lot of heat from state 4 to 1, which is proportional to the area underneath. So Q dot C is proportional to this area. And as we can see, in the evaporator, the temperature doesn't change. It always remains at -5 degrees Celsius, whereas the fluid changes its phase. And because the atmosphere, the surrounding cold space is a temperature 0 degrees Celsius, the differential of this temperature drives the heat transfer. So this is the heart of the refrigeration cycle, the evaporator, where essentially a very cold liquid boils off as heat is added. So at state 1, we have a saturated vapor. That's for an ideal vapor compression cycle. And then we compress it isentropically. Again, you're familiar with isentropic compression. The entropy remains constant. It's an ideal compressor. How does the compressor operate? It doesn't matter. As long as it's adiabatic and frictionless, it will be isentropic. From state 1 to 2, therefore, we compress the vapor. So when you compress a vapor, it is similar to compressing a gas, so the temperature also rises, pressure also rises. So at state 2, we have quite a high temperature. Let's say the temperature is 50 degrees Celsius, or let's say the temperature is 60 degrees Celsius at state 2. Now, at state 2, we have superheated vapor at a higher pressure, and at state 2, we send it to a condenser. What happened in the condenser? Just like a vapor power plant condenser, the vapor going through the condenser cools down. Heat has to be rejected. And suppose the outside temperature is, let's say, let's say outside temperature is 20 degrees Celsius. Then we have to make sure that as the vapor condenses, its temperature is never, it can never be below 20 degrees Celsius. So suppose this temperature is 25 degrees Celsius. So if the temperature at state 3 is 25 degrees Celsius, that means from 60 degree, the temperature will come down to 25 and temperature will never change. And the difference in temperature, 25 minus 20, will drive the heat transfer. So that's where our Q dot H will take place. So at state 3, we have saturated liquid at a temperature slightly higher than the atmospheric temperature. Again, we're taking TH to be 20 degrees Celsius and TC to be 0 degrees Celsius in our example here. So at state 3, the liquid at the end of the condenser, instead of using it in a turbine, what we use what is known as an expansion valve. In an expansion valve, what happens? The pressure drops rapidly, and because there is no heat transfer, you can show that if there is plenty of friction, it's possible to reduce the pressure. So it's not an isentropic expansion. It's quite the contrary. The pressure drops because of friction. We can show that enthalpy remains constant and the temperature drops. Again, we'll analyze the expansion valve in details again. We have done it in chapter 4 in your previous thermodynamics class. But again, we'll analyze this and show that enthalpy remains constant. So in summary, at state 4, we have a mixture of saturated liquid and vapor, and it boils in the evaporator, comes out as a saturated vapor at G state, which is compressed isentropically to state 2 to superheated vapor. From there, it's cooled at a constant pressure where the heat out, or Q dot H, happens. This is where Q dot C happens. So at the end of the condenser, the fluid after it condenses comes out as a saturated liquid at state 3, and there it expands in the expansion valve where enthalpy remains constant, we will find. And as a result, the constant enthalpy line in a TS diagram looks somewhat like this. Entropy is increasing while temperature drops, and we complete the cycle. Okay, let's go device by device, and then the picture will be clearer. Okay, so we start with our compressor, isentropic compressor. We understand the energy equation will be immediately clear. dE dt equals m dot H1, that's the enthalpy energy carried by the flow. M dot H2 is the energy that is coming out, plus Q dot, which is 0, minus W dot external. Steady state, so 0 equals m dot H1 minus H2 minus what is W dot external? W dot external is really W dot compressor, but W dot C is a positive number, so we must put the sign negative here. Again, this is following the Win-Hip sign convention, as you understand. Work in is negative, so W dot C is a positive number. When you say compressor power, 5 kilowatt, that means 5 kilowatt is going in. You don't need another sign to describe it. But W dot external here has a sign attached to it. It's an algebraic quantity. So we have to be respectful to the sign. And when we substitute W dot C, which is a positive number, we put the negative sign to reflect W dot external. In other words, W dot external equals minus W dot C. So therefore, the equation simplifies to W dot C equals m dot H2 minus H1, which is kind of obvious. The work going into the compressor equals the energy coming out minus energy going in. And if we use the entropy equation, it will be clear that entropy doesn't change in an isentropic, in an ideal compressor. Okay, so let's show that just for the sake of completeness. M dot S1 minus M dot S2. These are the different ways entropy can change as it goes through the compressor. Steady state, there is no net rate of change of entropy inside the compressor. No heat transfer, and an ideal compressor, no friction. And that tells us S1 equals S2. So in a TS diagram, we always, in an ideal system, state 1 will be always saturated, and we'll go isentropically as the pressure increases. So this will be the plot of the compressor in a TH diagram. Okay, let's move to the condenser. Again, let's quickly use the energy equation. In a condenser, heat is coming out, Q dot out or Q dot H, whatever you want to call it. So energy that goes in, energy that comes out, Q dot H will be the difference between that, and you can practically write it without going into the energy equation. What is Q dot H? The energy that goes in is higher than the energy that comes out with the flow. So the difference must be heat that is coming out, Q dot H or Q dot out, whatever way you want to describe it. And another thing, whenever there's a heat transfer in a flow, always resist from immediately assuming that heat transfer will affect the pressure. It doesn't. Heat transfer only affects the pressure of a fluid when it's in a closed chamber. And when the fluid is free to move, it doesn't affect the pressure at all. So because of friction, actually pressure may drop slightly, but we'll neglect that in an ideal condenser. So in a condenser, essentially it's opposite of boiling. So if I have a state 2 here, pressure remains constant, this constant pressure line, and at the exit of the condenser, it's always assumed that I have a saturated fluid. In other words, this is my F state. Okay, let's move on to the expansion valve. Okay, so let's go over the energy equation very quickly. The EDT, again, m dot H3 m dot H4 plus Q dot minus W dot external, right? If we neglect, well, for steady state the EDT equals 0, and if there is no heat transfer, of course there is no external work transfer here, no shaft electricity, etc. So therefore, as you can see, H3 equals H4. So expansion valve is called isenthalpic. Well, but as you can see, if we use the entropy equation, you can immediately see entropy will increase because the way the valve works is through friction. And we know friction can be greater than, whenever there's a friction and S dot J is greater than going to be 0, this is the second law of thermodynamics. It can be equal 0 for a reversible system. So steady state, no heat transfer, and immediately it's clear that S4 equals S3 plus a quantity that can never be negative. So therefore, this must be greater than S3. S4 equals S3 in an isentropic process like in a turbine or compressor, but friction is essential in this case. This is also known as throttling. What happens is called throttling. The flow is throttled. So in a throttling device, like an expansion valve, what happens is that entropy increases. So in the TH diagram, let me make a small diagram here. State 3 was the condenser exit state, saturated fluid, and pressure must drop. So we must be on this low pressure line, and entropy increases. So what happens is that we move to the right, and that's why it looks like this. Finally, let's analyze the evaporator. What happens in an evaporator is that heat is added, Q dot C, that's our cooling load. And the energy that comes in, energy that's carried out by mass, oops, the wrong way, energy comes in here at state 4 and goes out at state 1. So if we do an energy analysis of the evaporator, m dot h4 is coming in, m dot h1 is going out, plus q dot minus w dot. That's the standard energy equation, steady state, no external work. And we recognize that q dot and q dot c are equal through our Win-Hip convention because heat in is positive. Q dot c is going in. So we can substitute that here, 0 equal m dot h4 minus h1 plus q dot c, or q dot c equal m dot h1 minus h4. Obviously h1 will be higher than h4. So that's how we got our cooling load. And finally, W dot net in a refrigeration system vapor compression cycle is W dot C because there is no other work transfer, and that's what is going into the refrigeration system. So COP can be now obtained from Q dot C divided by W dot net. So now we have developed formulas for energy transfer on each of the devices. One thing I didn't mention that I routinely assume J and H are equal. Recall that J equal H plus KE plus PE, and we neglected the contribution of KE and PE in the entire analysis. We'll now go and solve a problem to get a more thorough understanding of this cycle. This is an ideal vapor compression cycle problem involving R12. Let's switch it to R134, a more common refrigerant. The two pressures of the cycles are given. One is 0.15 MPa and the high pressure is 1 MPa, which means at state 1 the pressure is 0.15 MPa, and at state 2 the pressure is raised to 1 MPa. If we draw the TS diagram, this is the lower pressure. So state 1 is saturated by definition in an ideal vapor compression cycle, and isentropically we raise the pressure to state 2. From 2 to 3 heat is transferred out, and 3 is again saturated liquid, and 3 to 4 isenthalpic expansion in the expansion valve reaching 4. What we are after is Q dot C. This is our Q dot C, how much heat is added on the evaporator, and this is our W dot C. So the tonnage of the system basically means Q dot C in ton of refrigeration unit, and compressor power, and their ratio is obviously the COP. So let's begin by finding the 4 different states, and we'll do energy analysis of each of the devices. So let's begin with state 1. First, let's list what we know. Pressure is given 0.15 MPa, and it's a saturated vapor. So X equals 1. So how do you find any property of a saturated fluid? That's very simple. H must be Hg at 0.15 MPa. So we go to the saturation table of R134A PC model. R134 is here. There is no pressure saturation table here, just temperature saturation table. So we look for 0.15 MPa. It's close to, in between these two, so it's closer to, okay, somewhere in between the two. So we are looking for enthalpy. So between 236 and 237. So let's say it's 236 point, let's call it 237. How about that? So we just write down 237 is our answer. And we might need entropy also. So at 0.015 MPa, entropy is somewhere between these two. How about 0.93? Pretty approximate, eyeballing. So entropy is 0.93. Let's go and verify these answers. We launch test calcs. Again, following the open specific branch, we'll find the vapor compression here, vapor and gas compression. We are following vapor compression cycles with PC model. That's our only choice. Click run, and here comes the test calc. Select the fluid R134A. State 1, pressure is known, 0.15 MPa. X is known to be 1, and I believe the mass flow rate was given to us to 0.04. So let's see what enthalpy we found. 238.8, 239, not bad, 0.938. So we're a little bit off, but that's fine. But at least we didn't make any big mistake. So let's go to state 2 now. What do we know about state 2? The pressure is 1 MPa and entropy is about the same because isentropic. So at 1 MPa, we first have to figure out where the state is. Is it superheated or a mixture or what? Of course, you understand from the diagram itself that if this is state 1, state 2 must be superheated. But you can prove it just to make sure. Find out the saturated vapor S. So if we find SF at 1 MPa and compare that to this, then we'll know for sure superheated vapor. So this is a good practice. It may take a little time. At 1 MPa, we want to find the saturated SG at 1 MPa. So this is 1 MPa, very close to 1 MPa, and you can see the value is about 0.904 or something, 9045. So therefore, you can see that S is greater than it's SG. So therefore, it is superheated vapor. So since it's superheated vapor, we can go and find the enthalpy by going to the superheated vapor table, knowing that S is 0.93 and pressure is 1 MPa. So we open the superheated table for our 134A and go to 1 MPa. Where is the 1 MPa table? Right here. And entropy is 0.93 in between these two, closer to the second line. So enthalpy will be closer to these lines. So it's let's pick 278, 268 and 280. So we pick a number close to 280, which is 278. So we go and substitute that value here, and therefore state 2 is now completely calculated. All that is left is state, there are 2 more states left. So let's go and calculate state 3 now. State 3 is simple, straightforward, because we know it is saturated liquid. So the pressure is the same, 1 MPa, and quality would be 0. So it's quite straightforward. We go and go to the saturation table this time again and try to locate 1 MPa line, and 1 MPa somewhere between these two lines, as you can see, 1 MPa. So H enthalpy becomes about 268, almost 268. And finally, state 4, we know enthalpy remains constant, so pressure is known, same as P1, which is 0.15 MPa, and enthalpy is 268. So we don't need to do anything. Already enthalpy is known. Let's go and verify that we didn't make a mistake. We haven't calculated even state 2 yet. State 2 is 1 MPa and entropy is the same. Of course, the mass flow rates are equal. So state 2 is calculated. State 3, pressure is same as P2 and X equals 0. Mass flow rate is the same. And finally state 4, pressure is equal P1 and enthalpy equals H3. Mass flow rate is the same. And we got about the same. No, we didn't get the same enthalpy. We made a mistake. Let's go and fix it. We go back and notice that what the mistake we made, I think we picked up H should be HF at 1 MPa. I think we may have picked up HG at 1 MPa. So we go back to 1 MPa line and enthalpy is here. Look, it's at 1 MPa, enthalpy between 102 and 105. So maybe 104 would be our guess. Again, going back, check, did you get around 104? We got 106. So that's more like it. So now that we have calculated and verified all our enthalpies, by the way, did we get the state 2 correct? State 2, we got an enthalpy of 278. Let's go and make sure. State 2, this is what we got. 278. So a TS diagram is a good idea to draw, constant pressure lines. It shows how the cycle should look like. Through state 3, if you draw a constant enthalpy line, you should be able to see 3 to 4. It's a difficult line to plot. It looks weird, but 3 to 4 is connected by constant enthalpy, as you can see. Coming back, all that remains now is to analyze our devices. Let me join this just for the sake of completeness here. So let's analyze the compressor first. Well, the compressor power is m dot h1 minus h2, and if we substitute the values, wait, no, it's h2 minus h1, sorry, compressor power is positive. It should be 2 minus 1, and now if we substitute the values, you can see that will be about 1.58 kilowatt. We already found m dot h2 h1. We can go to the device panel and calculate device A as the compressor, state 1 to state 2, and heat transfer equals 0. That gives us about 1, that's negative, that's external power, and the compressor power is 1.58, obviously. To find Q dot C is m dot h4 minus h1. Again, when you substitute the values, you can show that Q dot C is 5.28 kilowatt. Then if you divide that by 3.57, then we get in ton, which will be in ton of refrigeration. That turns out to be 1.5 ton of refrigeration. This 3.57 is just a conversion factor between ton and kilowatt. So therefore COP of the refrigeration system, which is Q dot C by W dot C turns out to be 3.33. Let's make sure these numbers are correct. So state A has been, device A has been analyzed. Device B is our condenser. State 2 to 3, heat is going out. There is no work transfer. Q dot should be negative number. In the enthalpy, in the isenthalpic expansion valve, what we got is at 3 it enters and 4 the flow goes out. There is no work transfer, and heat transfer also should be 0. When you calculate, that is what is shown. And finally, in device D, the evaporator, we have state 4 is the inlet state and state 1 is our exit state. No external work transfer, and Q dot is found. If you go to the cycle panel, you can just click calculate because we have calculated all the states, all the devices. COP is shown, and all the other quantities are displayed. If you click the super calculate button, it will create a detailed solutions for you, detailed solution result, as well as the test code which you can use for any future calculations. Also, you can do what if studies. Suppose you say, what if my fluid was not R134A? Suppose you say the fluid was R12, another refrigerant. All you do is to select the new fluid, press the super calculate button, and you can see the effect of that. Look, the COP is slightly lower, and you can see different quantities, how they respond to a change of variable. So that's the power of using test calc. You verify your manual calculation, and then you can do a number of what if studies. Okay, that is all for the ideal vapor compression cycle. We'll analyze a more complicated cycle in the coming module.